You could also still do a dot plot, a stem plot. In most cases on the AP FRQs, they are not going to make you graph. So usually, like what you're going to see today, they are going to provide you with a graph, and you just have to comment on, does it have skew? Does it have any outliers? If it doesn't, great, we move on. The big change between proportions and means is we are going in and we are using something called a t-distribution. So instead of there being just critical values z's, the only time you would ever use a z-test or a z-interval for a means question is if you know the population standard deviation. And in this case, you don't really know the population standard deviation because that is a very rare thing. Because if I know the population standard deviation, then that means I have to know the population mean. So it's kind of like a why am I doing this at all? One thing that came from confidence intervals is the test statistic is calculated differently. Unlike with proportions, you can't just say if it's 95%, it's always 1.96. This is something where we have to go in and we have to calculate something called a degree of freedom, and that was n-1. And so a lot of the time with the means, the conditions go a little bit faster, especially if you don't necessarily have to graph it, which you should not have to graph it, because you are not having to go through that check of large counts. So this was just kind of a summary of what we talked about, how we got to t-distribution in the first place. It's basically because we don't know a population standard deviation, so we're using a t-distribution. Now, the next thing that we kind of move into is significance tests in general. Whenever you had a significance test, you defined a parameter. Remember, for means, our parameter is mu. A lot of us are probably still used to writing the p equals. That is not the case. So if our parameter is mu, when I go to write my hypotheses, I'm going to have mu is equal to mu naught. It is always going to be equal to for the null hypothesis. For the alternative hypothesis, this typically comes from the question. Sometimes they think it's less than, sometimes they think it's greater than, sometimes they're just interested in, is it different at all? So that will come from what do they think is happening. Now, with what we do, one thing that becomes a part of the test statistic is knowing the null hypothesis value. So this is the null mean. And so we're going to use that to plug into our test statistic calculation. Now, again, I'm going to walk you through how this works by hand, and then we're going to talk calculator. Most of you are probably going to use your calculator. That is okay. It's just sometimes knowing the formula are helpful because of those multiple choice questions that pop up. Okay, we get our hypotheses. Once we get our hypotheses, we want to go in and we want to calculate a test statistic. So for the test statistic, it's typically going to be your statistic, which is going to come from your sample, minus the parameter, which is going to come from your population. So it's, and I'll show you the specific formula with the specific values we use in just a second, over, and a lot of the time we are using our standard deviation. There is going to be one slight change here, only because a lot of the time when you read these questions, we don't know a claimed population standard deviation. So when we do this, this is going to kind of revert back to being a standard error. Remember, the only reason we call it standard error and not standard deviation is because it's going to come from a sample and it's not going to come from a parameter. So population. Basically, at the end of the day, whether you call it standard deviation or standard error isn't going to make the biggest difference because you're probably not even calling it anything at all. Again, mostly going to your calculator, but that is why if you read anything on MATLAB or see anything online, it's referred to as the standard error for these t-distributions. Now, once you have your test statistic, in our case, it's going to be our t, In proportions, it was our z. Once you have that, you calculate something called a p-value, and we use that and compare it to a significance level. If you are not given a significance level, the most common one that is used is 0.05. If it's a question that they don't tell you what to do, you actually are free to do whatever you like. You can use 0.01, you can use 0.1. Of those three, you kind of get free reign, but your conclusion has to match. So say, for instance, my p-value was 0.03, and I picked a significance level of 0.01, then I should be failing to reject. So just make sure that your conclusion matches the significance level you selected. Pick 0.05. It's the most common one if you don't have one that's given to you. Now, that significance level, that alpha, is compared to your p-value. The p-value comes from the test statistic, and it tells us, and this is kind of the definition, the probability we get the statistic or something in the more extreme direction. The big idea here is if the null hypothesis is true. So a lot of what you'll see evaluating wise when it comes to a p-value is if the null mean, or if the true mean is 5, and that's their claim, the probability of me getting an X bar like this or more extreme is p-value. So it's basically just saying how likely is it for this sample to happen. Now, if the p-value is low, so when the p-value is less than alpha, you reject the hoe. So we will reject the null. And one thing that I always kind of relate to rejecting, you are going to have convincing evidence. If you are rejecting their claim, you have enough evidence to go against what they are saying. If my p-value is greater than alpha, we fail to reject the null. We do not have convincing evidence. We cannot go against what they're saying. It's high enough for me to believe that what they claim is true. So all of those same ideas around a significance test are the same. Same conclusions, same sentences. The only change is instead of finding a Z, we are finding a T. Instead of using normal CDF, we're going to use something called a TCDF. So let's go in and let's kind of specifically look at this one sample t-test for means. So T is going to be equal to X bar minus mu naught, and that is coming from the null, over the standard deviation over the square root of n. Now, again, most likely you're probably not going to have to use the formula yourself on an FRQ. This is something where if you do it by hand, this is coming from value minus mean over standard deviation. In our case, it's a standard error simply because instead of using a sigma, it is using an S, which represents a sample standard deviation. That is why it's called a standard error. Now, T is still going to have n minus 1 degrees of freedom. And just to kind of reiterate, but not make it a huge deal, if you happen to know the sample or the population standard deviation, then you would use a one sample Z test for means. This is going to be very, very rare. Like, this is never going to happen. The only time I would expect a question related to this at all is, when could you do this? And it's only if you know the population standard deviation. That is the only time you should use a Z anything for means. Once we have pulled our test statistic, we do actually jump to our calculator. We are going to use TCDF, which is going to be found. This is going to be in second vars, and it should be option number 6. This is going to work exactly like normal CDF. So instead of having the mean and the standard deviation, it does ask you for degree of freedom. The only reason being because every single sample size has a slightly different distribution based on the degree of freedom. But it works exactly the same way. And we'll kind of talk about directions you should go in based on your hypothesis in a second. So one thing I will say, because I do get this question missed often, there is a lot of dependency on the calculator, and it's fine. Yes, you can run the test. It's going to give you T, it's going to give you P, and that's great. There are a lot of people who miss questions where they say, the z-score is this, what is the p-value? And they give you no information like sample size or anything like that. So you can't actually use your stat test menu. The same thing could happen in means where they say the t-test statistic is this number, the hypothesis is this, what is the p-value? You have to remember that you can still use normal CDF and TCDF in order to calculate those things. Because we get so used to using the stat tests, we forget that this is even an option. There are times where the question is not something that can go into stat tests. When they give you just a Z or a T, you can't use it. So remember that they exist because oftentimes they are very easy questions, but they get missed a lot because people forget because we're so used to the calculator. So 3 conditions. We have random. We can either have random selection, which I will say is a lot less popular in quantitative data. It happens, like it does, but oftentimes you'll be dealing with experiments, and you, instead of having random selection from the population, you are dealing with volunteers, and the volunteers are not randomly selected. So a lot of the time in the experiment itself, you have to go in and randomly assign either them to a treatment, or you have to randomly assign the order of the treatments if you're doing something like matched pairs. So if the sample size is greater than or equal to 30, we can say the central limit theorem tells us it will be approximately normal. If the sample size is less than 30, we have 2 options. We can either be told that the population is normal. If the pop is normal, the sampling distribution is normal, or we can graph it and see from our histogram or dot plot or stem plot that we have a normal distribution. So all 3 conditions are exactly the same from confidence intervals. The really nice thing about this compared to proportions is there's no, well, you have to use p hat and not p, and in this one you're going to use pc. It is literally the same exact 3 conditions, the same exact. They are not changing. They are the same exact thing. So you don't have to decipher between 1 sample, 2 sample, or 1 sample interval, 1 sample test. The 2 sample ones will change only because you have to do them for both populations, but they are still the exact same 3. So let's go in and let's do some hypotheses. The alternative, it can look one of 3 ways. It could be less than mu naught. It could be greater than mu naught. It could be not equal to mu naught. These first 2 are one-sided or one-tailed, and you'll see why in just a second. This is a 2-tailed test, 2-sided. So whenever we convert things to a test statistic, they are going to center around 0. So as I start to standardize my data, and in the less thans, you are always going to get a negative t-star because you think that your number is less than the mean. In the greater thans, we're going to get a positive t-star. And then in between, you will technically have both a negative and a positive, which makes it the 2-tailed. And based on the description of a p-value, it's always in the more extreme direction. So it's always shading outside. Now, one thing about this, these shaded regions, they are your p-value. They are, if the null were true, how likely is it for a sample like this to happen, or something more extreme? Because if it's more extreme, it proves them more wrong. So when we go in to calculate these p-values, we do have to enter in our lower and uppers. So if it's a less than, it's negative infinity to the negative t. If it's a greater than, it's t to positive infinity. When it's a two-sided test, you kind of get the freedom to choose which direction you want to find. I usually base it on when I've calculated the test statistic, is it positive or is it negative? If it's negative, I just go from negative infinity to negative t, or if it's positive, I do the t to positive infinity. The only thing I will say, if you are doing this by hand, when you find one side, you must double it. So you find either the lower tail or the upper tail, and because of the nature of symmetry and this being by the time you've checked conditions, a normal distribution, or approximately normal, we have to remember, if I find one side, I have to double it to get the other. You can technically find them separately, but it just would be a waste of time because it's symmetry and they are the same area. But if you're doing it by hand, do not forget to double it. If you are doing it in the calculator using stat tests, you do not double. The calculator, when you tell it to do a not equal to, it doubles it for you. So don't double what they give you from the stat test menu. So let's go in. We've got 2 examples today, so it shouldn't take us too long. One is going to be just the plain, straightforward one sample test. The other one is going to kind of revert back to that matched pairs design we talked about at the end of the last set of notes. So in example 1, at the Hawaii Pineapple Company, managers are interested in the sizes of the pineapples grown in the company's field. Last year, they said the mean weight of pineapples was 32 ounces. So that is what we're kind of comparing to. That's what ends up being our null mean. And then a new irrigation system was installed. They want to find out, they're going to go out, they're going to select a random sample of 50 pineapples. They got a mean of 31.935 ounces, standard deviation of 2.394 ounces. Does this data give convincing evidence? And this line I'm always going to kind of highlight because I want you to know, if you see this, you are doing a hypothesis test. Usually it's just, do you have enough evidence to go against what they are saying? And that is the whole nature of a hypothesis test in general. Do they have enough evidence that the mean weight of pineapples has changed? So the big key word here is changed. They don't necessarily care, was it higher, was it lower? They just want to know, is it different from the 32 ounces we believe it to be last year? So I'm going to go in, I'm going to do mu is equal to, we are doing mean weight of pineapples. And I'm going to be specific because we are not sampling pineapples all over the world. I'm going to say in this field. You could even say at the Hawaiian Pineapple Company, but that's longer words than in this field. With the parameter defined, I am now going to go in and I'm going to write my null and my alternative. Remember, you have to break the habit of writing P equals because we are dealing with means. So this is mu is equal to their claim of 32 ounces, their last year value. And they're just interested in, has it changed at all? So mu is not equal to 32. So now that I have my parameter, I have my hypotheses, I'm going to go in, I'm going to check my conditions. They did say they did a random sample of 50 pineapples. And here in the first box, you can also define your alpha. We could say alpha is 0.05 because they didn't give us a specific one, but I'm just going to put that into my conclusion so you don't have to write it twice. Random sample of 50 pineapples. Then we are going to go in and we're going to say it's safe to assume that there are more than 500 pineapples in this field. And And I'm just going to come in and I'm going to say safe to assume. And because my sample size is so large, it's 50, I don't have to graph it. I don't have anything to graph anyway, but I can just go in and say, since 50 is greater than or equal, that looks like almost like a 60. I'm going to rewrite it. 50 greater than or equal to 30, CLT says sampling distribution. And this is, so whenever we do confidence intervals, we typically relate the sampling distribution to the sample. This is going to be, we're trying to represent the population. So I'm going to come in and I'm going to say mu is approximately normal. Whenever we were doing this for proportions, when we were doing the confidence intervals, we used p hat. And when we were doing the hypothesis test, we use p. So it's kind of the same thing where when we did the confidence interval, we used x bar because that's based on the sample. And when we do the hypothesis test, we use mu because that is the population. Now, once we have kind of our conditions in place, we've checked everything, we can go into the calculation. For my people who are solely going to be calculator based, and you know if you are already, one sample, you have to name it. One sample t-test for means. And yes, as unimportant as it seems, if you wrote z-test instead of t-test, they would not give you credit for it. It has to be a t-test for means. Now, I'm going to go in, I'm going to calculate the test statistic first. So t, one thing about t, it is coming from, and you don't have to rewrite this, but I am just because it's not on the same page. This is the base formula for a test statistic. So I'm going to plug in what I know. We know the mean is 31.935. We know the claim is 32 because we're trying to see how far away is our sample from what they think it should be. And this is how we calculate that distance. Standard deviation is 2.394 over the square root of n, which is 50. I plug all of that into my calculator, and when I do this by hand, I use the alpha y equals fraction if I'm putting fractions within a fraction, only because it gets to be a little wonky when you have to make sure your parentheses are correct. So I did negative 0.1920. That is my t-test statistic. So now that I know what my test statistic is, and if you need to label this, because I can tell you MATLAB is probably going to ask you what is the test statistic, and then you're going to ask yourself what is the test statistic. It is t. That is what they want. So now that I have that, I need to go in, I need to calculate my p-value. So what I'm going to do, because I am doing a difference test, so it can go in either direction, below or above. Since my test statistic is negative, I'm just going to go in, and for the p-value, I'm going to do TCDF, and I'm going to use a lower of negative infinity. I'm going to use an upper of the negative 0.1920, and my degree of freedom is going to be 49. And that's one of the rules we just talked about at the very beginning. It's sample size minus 1. So my sample size was 50. I subtracted 1 from it. I got 49. Now I'm going to go to my calculator really quickly. Oops, it was not supposed to open the whole way. Let's see. Calculator. Let's do this. Calculator. I'm going to go to second vars down to option number 6. And then I'm going to put negative infinity, negative 0.1920, degree of freedom. You should have prompts. I kind of have the prompts in a really funky place on this digital one. And then you should get a p-value of 0.4243. Now, the thing to be careful about here is this only represents, and you don't have to draw a picture, I'm just drawing it for the sake of us looking at this in terms of notes. This 0.4243 only represents the lower tail. So if I want to get the entire p-value when it comes to a test of difference, I have to make sure that I remember to take whatever I get from one of them and double it. So my p-value is going to be 0.8486. Now remember, and I'll show you the test because I am only going to use a calculator on the second example. Whenever you use the stat test options for tests of difference, you don't have to double. That would give us the 0.8486 exactly on its own. So don't worry about that. You don't have to do any of that if you're going the calculator route. But now that I have my p-value, I need to come in and I need to interpret. This is literally the same exact sentence we've been doing. Since the p-value of, and that's where I usually fill in the 0.8486, is greater than alpha equals 0.05, we fail to reject the null. Anytime you fail to reject the null, you do not have convincing evidence. There is not convincing evidence. Or you could even go as far if they use like significant evidence, or is it statistically significant? That just would mean if you rejected. We did not. There is not convincing evidence. And this is where I go to the question and I kind of see how I'm going to rephrase what they have. There is not convincing evidence the mean weight of pineapples in this field has changed. So a lot of it is just coming in and putting in that context, but the basic outline is the same as proportion. So the only thing that I filled in that I would not change problem to problem, I changed greater, I did my alpha level, we failed to reject, there is not, and then the context of the problem. This is what gets added in. But it is the same decision making, it is the same conclusion, nothing changes. Your p-value, at the point where you have a p-value, you are interpreting it exactly as you would if it was a proportions question. It's just the context is going to look different. Okay. Remember, the last thing we talked about in 7.1 was matched pairs. And we said matched pairs is an experimental design where I have so many contributing factors that if I were to kind of compare a person to like a group of people to a group of people, there's so many things at play. Like one of the examples in your math lab, I think, was like husbands and wives. Like if I wanted to see how healthy each one was eating, putting all of the husbands in one group and all of the wives in one group doesn't do a ton for us because people are so drastically different. But I can have like husbands and wives paired together because a lot of the time they do have very similar qualities. They're close to different types of food. They eat at home versus they eat out. So all of those things, because they play factors, we go into matched pairs instead of treating them as two completely separate groups because of all of those other factors that can affect what we're looking at. So this one is a fun one. They are trying to find out if caffeine-dependent people are more depressed than non-caffeine dependent people. So researchers designed an experiment to study the effects of caffeine withdrawal. They got 11 volunteers, and that's a big part for us when it comes to how we're going to check our conditions, because we cannot say that people are randomly, thank you, I haven't. We cannot say that they are randomly selected. So what they're gonna do is each subject, each of the volunteers, they are going to spend 2 days taking their normal caffeine, and then they're going to take a test on depression, and then they're going to spend 2 days with a placebo that has no caffeine, and then they're going to take their depression test and they're going to compare the scores. Now, one thing that's going to be important here, the order in which the subjects took caffeine and the placebo was randomized. So that is going to be enough for us to say, okay, we can check off the random condition. The depression scores also, another part that's going to play into how we write our hypotheses. Higher scores show more symptoms of depression. So they gave us a table that has both their initial or their placebo score and their caffeine score, and they gave us a row that shows a calculated difference. Remember, when you have identified it as matched pairs, you only care about the row with the calculated difference. Now, I will say sometimes they don't calculate the difference for you, but it is something you can do within your calculator if you wanted to. You can do L1, L2, and then in L3 put L1 minus L2. But truthfully, you can just subtract them. Just subtract the values, get your calculated difference, and then go about it that way. So when I look at this, they have already decided it's placebo minus caffeine. So I am going to go with what they have done so that I don't have to do any extra work. Now we have does the data provide convincing evidence? And our significance level is now 0.01, so that's going to be important when we conclude. And they want to see, does caffeine withdrawal increase depression score? So that means that their scores when they are having the placebo are higher than their scores when they have their normal level of caffeine. So I'm just going to make a little note here. Placebo scores need to be higher than caffeine scores. That looked spelled wrong, but I think it is spelled correctly. Okay, so let's define our parameter. Typically for matched pairs or paired data tests, we use mu of D or mu of diff, whichever one you prefer. You technically could still just use mu, and I don't think they would dock you for it. This is the mean difference in depression scores. And I'm just going to specify placebo minus caffeine. If you were calculating and picking yourself, you would be the one you would absolutely have to say, I did placebo minus caffeine. I think it's helpful either way. Then I'm going to come in and I'm going to write my null. I'm going to write my alternative. For the null is that there is no difference between the two treatments. So if I want there to be no difference, mu of D would have to be equal to 0. And anytime you are doing a significance test for matched pairs, this is going to be your null, because this would say, when I subtracted these two numbers, I got 0 because they are the same two numbers. There's no difference between whether they had the placebo or whether they had the caffeine. Now, the part that a lot of people get wrong is deciding, now that I have my null, I have to figure out what direction I want my alternative to go into. So with how we did it, we did placebo minus caffeine. We want placebo to be the bigger number. So think big number minus a smaller number. That should always give you a positive number. So we want this to be bigger than 0. Think big minus small. If I had done caffeine minus placebo, then I would want that second number to be bigger than the first, which would make us a negative. So how you kind of decide with your subtraction is how you decide what direction your inequality should face. If it's just a difference, then you don't have to think at all. It is what it is. But that is because I want the placebo to be bigger. So now I'm going to run through my conditions. These are going to look a little bit different than we're used to seeing. I'm going to say order of treatments randomized. And that's going to cover our basis for random. I'm going to say, now, This one is a little bit of a special case. We did use volunteers, so it's not like we randomly selected from a population. Anytime you're kind of doing an experiment and you have not randomly selected, we just kind of say the subjects are independent of each other. So I'm going to go in and say the subjects are assumed to be independent. The only reason why I'm not going to write 10% is we don't, like, yes, they are representing caffeine dependent people, but we don't know what that population necessarily is. And so anytime that feels kind of funky, that is when you want to revert, and it's most likely going to be an experiment because that's when you have volunteers. Let's just revert to saying we're going to assume that they are independent. The third thing that we should be checking is our distribution normal? So I went ahead and saved us the trouble. I am going to still advise that you put this data into your calculator because that's how we're going to run the test. But what I did is I took the all of the calculated differences, so what I have highlighted in that last row, I put it into L1, and then I graphed my histogram. I went ahead and included the window that I eventually changed it to after I hit Zoom 9, just so you can kind of see what that histogram would look like. This would be something where they would most likely provide you with a graph. So all you have to do is to be able to look at the graph, double check that there is no strong skew or outliers. And it doesn't look like there is any, and a lot of the time on AP grading, they emphasize the word strong because sometimes there is some slight skew. As long as you're not seeing a very extreme tail or an outlier, we just say like, it's fine. We're gonna use our T procedures. So no strong skew or outliers. So sampling distribution of mu is approximately normal. Now, I am going to fully go the calculator route on this one because I don't recommend, if you only have data, using the formula because you have to do two things. You have to first calculate the X bar and standard deviation, and then you have to go in and use T to find p-value. If you are going to have data only, it's probably in your best interest to just run the test in the calculator. So I'm going to go ahead, I'm going to write a 1 sample t-test. Here is the change. It's going to be 4 paired data. And then what I'm going to do is I'm going to jump to the calculator. So this is going to be stat. This is our stat button. This is going to be tests. And it should be test number 2, the t-test. And we are going to be on the data side of things. So it does have the same features as the t-interval. It does have data versus stats. Stats would be like what we had in example 1, where they gave us summary statistics. Here, when I go to, and I'm going to open up my calculator just so we can see it side by side. When I go to my stat test, oops, let me get out of that, stat test number 2, and I go to the data side of things, it asks me, what is my mu naught? That is, what is your null value? What is your list? What is your frequency? What is your alternative? When you go in for the less thans or greater thans, make sure that the inequality on your paper is the same direction as the inequality in your calculator. That is another big mistake that a lot of people make. So I put mu naught as 0 because that's what's in my null. I picked the greater than because I want it to be positive. And then I'm going to hit calculate. And usually my recommendation is to write everything you get from this window down. So 4.5030, P is equal to, don't forget that if you see an E to anything at the end of your value, you have to move your decimal that many places. So this is going to be 0.0006. And I usually will always say it doesn't hurt to write down the summary statistics. This again is mostly just to cover all of your bases, because potentially you could type something in incorrectly, and if you only report a T or a P, we are not going to know why. Why was it wrong? But if I can look at your summary statistics and I can see, okay, they have an incorrect X bar. For some reason, it is 5.2 instead of 5.8. I can kind of pin down where I think it's going wrong. And a lot of the time, if it becomes an FRQ where they are trying to decide between, do we round them up to a 3 or down to a 2, little things like that, it's like way behind me, are what kind of make the difference. I think they are trying to move away from having graders actually decide rounding up or rounding down, but I don't think it's fully integrated yet. So it's still a possibility. Now, to conclude, since the p-value of 0.0006 is less than alpha equals 0.01, we reject the null. There is convincing evidence, and this is where I revert back to the question. There is convincing evidence that caffeine withdrawal increases depression score. Now, this is one where I would say that last little statement they have is important, because again, you are dealing with volunteers. And so I cannot take this test and apply it to the entire population. I can only apply my results to subjects like these. And that typically comes from anything where you are sampling from or you only have volunteers and you didn't actually get to sample from the population.